My name is Wey Xuan. In this presentation, we'll be discussing the exploratory data analysis, EDA, conducted on our chosen dataset, which is related to sleep efficiency. Our primary objective is to explore how various lifestyle factors such as exercising, caffeine, and alcohol consumption can influence sleep efficiency. The dataset is sourced from Kaggle and provided by Milike Chi, a quality engineer at Yaris Group. It consists of 452 records and 15 features. The features are categorized into three main sections. First is demographic features such as age, gender, and ID. Sleep details including sleep duration, sleep efficiency, REM sleep percentage, and more. And lastly, lifestyle factors like caffeine consumption, exercise frequency, and smoking status. Now we'll be going through our R code. First, we load the dataset by using the read CSV function. Then we'll be able to preview the dataset using the head function. This will show the first few rows of the dataset. After that, we clean the data by removing the ID column, which is not necessary for the analysis. This helps us to ensure that our analysis focuses on relevant features only. Finally, we generate a summary of the dataset using the summary function. This calculates the key statistics such as the mean, median, standard deviation, minimum, maximum, and percentiles for each feature in the dataset. These statistics can help us to understand the distribution of values and identify any data issues within the dataset.
My name is Choo Jia Qi. In this part of the presentation, I will discuss the issue identified in the dataset during our analysis. The first issue identified is missing value in the dataset. Missing data can occur for various reasons, such as incomplete data entry or error during the data collections. Using sum_is.na function, we found a total of 65 missing values. The column with missing value were listed using the apply function combined with any NA function. For example, the dataset shows missing value in features such as the awakenings, caffeine consumption, alcohol consumption, and exercise frequency. To address this, we access data skewness using the moment library to determine suitable imputation methods. For normally distributed data with skewness close to 0, such as the awakening with the skewness of 0.49, mean imputation was applied. For skewed data with skewness greater than 1 or less than -1, such as the caffeine consumption with the skewness of 2.13, median imputation was chosen to minimize the impact of extreme values. We can compare the summary statistic before and after imputation using sum_is.na function to check if any missing value remains. The second issues involve outliers, which are data points that deviate significantly from others. For instance, unusual values were found in the sleep duration, sleep percentage, and caffeine consumption columns. Outliers can skew statistical measures and lead to misleading results. Box plots were used to detect outliers, and methods like median imputation or capping were applied to handle them. For sleep duration, the median method replaced outliers, which are 5 and 10, with the median value of 7.5 to preserve the distribution. For caffeine consumption, the IQI method kept extreme values, which are 200 at the upper limit. Similarly, for deep sleep percentage, capping outliers, example 18, ensure values stay within a consistent range, such as a minimum of 25%. After this, we can check if there are any remaining outliers using the box plot stat function. And then the third issue we check for is duplicate values, where identical rows could occur multiple times in the dataset. Duplicate values can lead to inaccurate conclusions. However, after analysis using the duplicated function in R, we found that there are not duplicate records in our dataset. This ensures that each record in the dataset is unique and no further action is required for this issue.
Hi, this is Kian Ming here. This histogram of awakening shows how often individuals wake up during sleep. The histogram is created using heads function with awakening column as input. We can use main parameters to the title, the chart, and X-lab to label X-axis as the number of awakening. The bar are colored orange with co-parameter, and the black bar border black help separate each bar clearly. This visualization highlights the distribution of awakening, allowing us to observe whether most individuals have a similar number of awakening or if the data is skewed. This box plot of sleep duration represents the variability in the number of hours people sleep. The box plus function is used to generate the plot with the sleep duration column as input. The main parameter sets the title, while ylab labels the y-axis that indicate the unit of measurement hours. The box plus highlights the key statistical features. The median is shown as the central line between the box. The interquartile range is represented by the box, and the whiskers extend to the typical data point. Any dots outside the whisker are outlines indicating unusual sleep patterns. This plot is particularly useful for identifying reliability and consistency in sleep duration. We aim to visualize the relationship between exercise frequency and sleep efficiency. The coding process begins with a correlation test using core-test function to calculate the Pearson correlation coefficient and p-value, which quantify the strength and significance of the relationship. Next, we use ggplot2 library for visualization. The AES function maps exercise frequency to the x-axis and sleep efficiency to the y-axis. The jump point function added to the blue scatter point to represent individual observation. Finally, we use the jump smooth function to overlay a rate regression line showing the trend in the data. The plot is labeled with labs for clarity, and we apply the temp minimal for a clean, professional appearance. This could help us clearly see how exercise might influence sleep efficiency.
And that is all for our presentation. Thank you.